Hi, my name is Shinji Watanabe. I'd like to discuss several applications and trends of self-supervised representation learning for speech processing toward zero-resource speech processing. This section composed of 4 subsections, including unsupervised speech recognition, ASR-TTS technique, zero-resource speech technologies and challenge, and textless NLP. Let me first describe the overview of this section. Previous sections mainly discuss the effectiveness of SSLR for downstream tasks with the paired data. However, this section relaxes this condition. This section introduces several applications of SSLR by using the unpaired data, and we introduce the following 4 directions as I mentioned before. Now I move to the explanation of the first topic, unsupervised speech recognition. In unsupervised speech recognition, we try to build an ASR system by using unpaired training data. This is a very difficult problem in general, but the recent progress of deep neural network-based generative adversarial network, GAN, can achieve this training. The basic idea of the GAN-based speech recognition training is like this. First, we generate the token ID sequence from the audio-only data. In addition, we have the text data. We trained an ASR system to generate a phoneme sequence. Here, the ASR system is regarded as a generator. Then, we also obtain the real phoneme sequences from the real text data with a pronunciation dictionary. By using a discriminator to distinguish real or generated phoneme sequences. This is a typical GAN system where the ASR generator tries to fool the discriminator. Note that this training process does not require the paired training data. By using this training iteratively, we can gradually improve the ASR system. Also, note that self-supervised model has an important role as a feature extractor for improving this training. Now I explain the experimental result. Unsupervised speech recognition has been studied with various researchers. This result summarizes the timid phoneme error rate trend with various approaches. As you can see, the performance was boosted when we use a self-supervised learning representation based on WAV2BEC 2.0. This result also shows the performance in the LibriSpeech benchmark. The light purple color bars show the performance of various state-of-the-art techniques by using the paired data or by combining the paired data and self-supervised or semi-supervised method. Surprisingly, the recent unsupervised speech recognition based on WAV2BEC2U achieved a comparable performance in the state-of-the-art system 3 years ago. And note that this WAV2BEC-U does not use any paired training data. Now I move to the second technique called ASR-TTS techniques. This technique is not fully based on the self-supervised learning representations, but the goal of using unpaired training data is the same. Also, this technique has the explicit intermediate representation based on the ASR output in the ASR-TTS pipeline and the TTS output in the TTS-ASR pipeline, respectively. This ASR and TTS output can be regarded as an explicit information of the self-supervised learning representations. Therefore, we explain this ASR TTS techniques in this section. First, we can summarize the role of the ASR and TTS systems. ASR output text data given the corresponding speech data. Similarly, TTS is an inverse problem and output speech data given the corresponding text data. Now we consider the combination of the ASR and TTS systems in a cascade manner. In this case, after the ASR process, the following TTS system using the text output as an input and generate the speech data. In this cascade system, we can find an additional loss function that the input of the ASR system and the output of the TTS system is consistent and close to each other. Based on this consistent loss, we can train both ASR and TTS systems only with the speech data. The intermediate text data can be regarded as a latent representation like the other SSL representations. This consistency loss is also constructed by changing the order of the cascade systems. If we consider to combine the TTS and ASR systems in a cascade manner, we can design an additional loss function between the input of the TTS system and the output of the ASR system. Note that this training system is inspired by various neuroscience, speech production, and speech perception studies. The importance of joint modeling of speech recognition and synthesis without the paired speech and text data are supported by various theories, including phonological loop, speech chain, motor theory, and so on. This ASR-TTS framework is first advocated as a DNN-based speech chain model by researchers in NIST. This is the first success of joint training of ASR-TTS and TTS-ASR loops. The first version of this work is freezing TTS parameters while estimating ASR parameters and vice versa to simplify the training scheme. Our group is also working on a similar direction motivated by the above speech chain study and the cycle consistency training developed in computer vision and neural machine translation. This work jointly optimizes both ASR and TTS parameters. Although we faced on the difficulty of obtaining gradients, especially after ASR, due to the argmax operation, we can solve this issue by using reinforce or gamble softmax. Note that this framework does not require the unpaired data in theory. However, the current implementation requires an initial ASR and TTS models trained with the paired data. Now we move to the experimental result. The following experiments show the libre speech result. In this setup, we use 100 hours of the paired data to train both ASR and TTS models first. Then we use the unpaired 360 hours of the audio-only or text-only data to jointly fine-tune both ASR and TTS models based on cycle consistency training. As you can see that by using the audio-only and both audio-only and text-only data, the ASR performance is significantly improved from the baseline. Note that this method can also improve the TTS quality. In this example, the TTS system with the initial epoch does not well generate the appropriate speech signals. However, after several fine-tuning, the TTS system started to generate reasonable speech signals. Let me play the audios. This is the initial epoch result.
It's anarchically. Accents if you like to represent.
This is the final epoch result.
Has never been surpassed.
I believe you can listen the TTS quality improvement, which comes from joint training of ASR TTS. Finally, the TTS ASR system gained more attention as a data augmentation technique. For example, by using various text-only data and speaker embeddings, we can generate huge amount of paired training data augmented by these variations. Currently, a lot of studies have been done in this TTS-based data augmentation techniques. In this presentation, I introduced the experimental result conducted by Kyoto University. The experimental result is based on the corpus of spontaneous Japanese, CSJ. Similar to the cycle consistency training case, they used 247 hours of the paired data to train both ASR and TTS models first. Then, as an unpaired data, they used the spontaneous lecture text, which correspond to 281 hours of the speech data. The experiment showed that the TTS augmentation, especially multi-speaker TTS systems, improve the performance from the baseline system. In addition to this direction, there are several variants of this study by using the speech feature and the phoneme to augment the paired data. Now I move to the explanation of the zero-resource speech technologies and their challenge activities. The zero-resource speech technologies aim at discovering linguistic concepts from audio only without using corresponding text data or lexical information. The example of the linguistic concept is phoneme, word, syntactic structure, semantics, and so on. These technologies of discovering linguistic concepts from audio-only data is inspired by the infant learning process. The goal of these technologies is to build spoken dialogue systems in a zero-resource setup for any language. However, to realize these technologies, there are a lot of difficulties. As you can easily imagine that it is very difficult to build a dialogue system only from the speech data. So we need an appropriate milestone to realize this challenging goal. Also, these technologies require the common benchmarks to compare the various technologies. We also need to develop appropriate evaluation metrics, as it is difficult to map the obtained results with actual phonetic linguistic representations. To tackle these issues, the Zero Speech Challenges was launched to guide the community for this research direction. From now on, I'll briefly go through the overview of the Zero Speech Challenge series. If you want to know more about the details of each challenge outcome, please also check the reference. Zero Speech Challenge 2015 is the first challenge, which focuses on building an acoustic model without using any linguistic annotations. As an evaluation metric, ABX and F1 scores are used. The data is based on the Bakke corpus of conversational English and the song section of the NCHLT corpus of South African language. In this initial challenge, people were mostly working on the generative model based on Dirichlet process Gaussian mixture model and other clustering techniques. Also, the majority of the system is based on a top-down system, which is initiated by the spoken term discovery system and followed by a neural network with pseudo-label targets, aiming for extracting the bottleneck features. Zero Speech Challenge 2017 focused on building an acoustic model with unseen language and speaker aspect. The evaluation metric is similar to a previous challenge based on ABX and F1 scores. The data has more language variations. The majority of the system is based on the top-down system that I described before. In Zero Speech Challenge 2019, the challenge starts to cover the ASR and TTS models without text, which covers the input and output modules of a dialogue system. In addition to the previous metric, TTS quality measures were introduced. Based on this challenge, the various autoencoder techniques are developed to perform TTS. The recent Zero Speech Challenge extended the application for spoken language modeling tasks. In addition to the phonetic evaluation based on ABX or F1 scores, additional lexical, syntactic, and semantic metrics were introduced. Also, self-supervised learning representation based on CPC, APC, and Hubert have been actively studied. Zero Speech Challenge has been significantly contributing to the progress of self-supervised learning representation by providing us the common benchmark, evaluation metrics, and technical comparisons. Finally, I will explain about textless NLP. As you know, pre-trained language models, including BERT and GPT-3 in NLP, show great success in various NLP tasks, including natural language understanding, question answering, and so on. In these applications, autoregressive models show the powerful ability to predict future words. This is one of the valuable applications of self-supervised learning. The question here is whether we can apply a similar methodology to the speech-only data. To realize it, one possible direction is to use a pre-trained audio model, including Hubert or Waldbeck2, to generate a large amount of discrete symbol sequences from the audio. After we obtain the discrete symbol sequences, we can make a speech version of a pre-trained language model. A generative spoken language model, GSLM, is one of the first tasks to realize a speech version of pre-trained language models obtained by a large amount of speech corpora. The structure is similar to the pre-trained language model in NLP as I shown before, and we can realize various spoken language processing tasks by providing a query or pre-training and fine-tuning strategy. I'm playing the example of GSLM provided by the researchers in Meta.
When an aristocracy carries on the public affairs, its verification there may be in science, the connections of the valley to which it was called upon to lecture, conferring on similar descriptions of opinion, and in other instances which appear to have never exceeded the same results. It cannot be found that the notion of the most ideal opinion is the popular notion of the edifice, nor is the susceptible possibility of introducing the same state of the continental character. The scope of the theory of the notion of the When an aristocracy carries on the public affairs, it's coming to the chronicles of the public jurisprudence as to what is observable, not naturally demanded of it, by the way in which postal axes are adequate delayed by freemen, and especially kindering the same stock. No body of postal acts has ever been demanded to labor, and any stock was personally adequate to labor. End of section 19.
As you can see from this example, Similar to the pre-trained language model demonstration in NLP, GSLM generates a natural speech continuation given speech query. Note that the model is extended to generate spoken dialogues with prosody and emotion controls. Let me summarize this section. This section reviews the unsupervised speech processing applications, including unsupervised speech recognition, ASR TTS framework, various zero-speech challenge technologies, texture-less NLP, and so on. The performance of these applications are boosted by SSLRs. Also, zero-speech challenge sheets provide the milestones of SSLR's technique. Thus, the progress of SSLRs and unsupervised zero-resource techniques are closely related. This is the end of my section.